I go to class required. Yeah, the discussion is like they posted the trailer, but it's like right now they the data stuff that I'm supposed to be. No, it's like think about yeah, I think it's kind of world bit. Yeah, it's like sometimes they say there's library.
Okay. We can find our seats. Welcome, everyone. Thanks for being here. Our second lecture of the spring 2025 lecture series. Another good one. I just wanted to say a couple notes here up at the top. You've read our land acknowledgement, but I want to thank AIA Potomac Valley again for their work in being the liaison between us and the national level AIAs so that any architects in the room will be getting continuing education credits. So we appreciate their help as always with that. I always want to note to the students as well, if you wouldn't mind registering your attendance here with this QR code and then doing the simple registration reminder. You do not need to add your photo to that. And I guess while we're waiting, you can, maybe is that a maze? Can you actually find your way through that? I don't think it's possible. Maybe, maybe not. Good. And so before we get to our guest, there's a couple of folks here who are going to do some introductions. Here's one of them now. But we'll start with Lindsay May to say a couple things about the event that happens right after this lecture.
Hi, everyone. My name's Lindsay. If we haven't met, I'm the director of the Scalable Gallery and the Associate Dean of Academic Affairs. And we're really excited for after the lecture to host the opening of the exhibition outside. So join us to check out inside the Scalable Gallery all the work of LTL. There'll be food and we'll be hanging out for a little while. So also I'll note that this is the last installment of the exhibition we're seeing. It's been at over 10 schools and institutions. So we're really grateful to Paul and LTL for bringing it here and letting it end its journey. And I will pass it to Adam.
Hi, for those that you don't know me, my name is Adam Bresnick. I was an undergrad here a couple of years ago, and I was the key distinguished professor thanks to Brian Kelly, who's in the back, 3 years ago. And this year I'm teaching a 601 studio with Michel Lambracos, together with Madrid and Tetuan in Morocco. Paul and I went to Princeton together a couple of years ago as well. And it's great both to be back here in this auditorium and to be back at Maryland and to be able to introduce a friend from graduate school. I wanted to say a word about generosity because when I think of Paul Lewis, I think of generosity. So Paul did his undergraduate work at Wesleyan University, and I believe one of their earlier projects is a dormitory building there. Mid-career projects.
Yeah, but that's okay. You're being
Okay.
very generous.
And thank you. And then he did his master's degree at Princeton, where we coincided. I'm a little bit older. Paul was defined by his generosity. So even as a student and a colleague, he would share, images, references, knowledge in a way that I think is still represented in his work. I mean, I follow, from afar, from Spain, I follow the practice of LTL, and to me, it was dramatic. The first time I ever returned to the US from Spain, I went to visit Paul, and he and his entire office were doing the punch list work on a restaurant that they had designed in Manhattan. And it was impressive to me, that generosity, that the office, that instead of just drawing the architecture, was actually there painting and sanding and screwing and maybe screwing, but tightening screws. That sort of cohesive and coherent way of looking at architecture as something to be designed and implemented and then shown and taught and shared. And the fact that this exhibition as well is accompanying the lecture today seems to me key to the sort of whole concept of generosity as a way of being and a way of practicing. So that's sort of my interpretation of Paul Lewis and LTL. I think really looking forward, I've never heard him lecture. So I think it'll be really an interesting experience. And thank you guys for having me here as well. And thank you again to Mohammed, I'm not sure if he's here today, for being here this semester as well.
Thank you, Adam. Thank you, Lindsay. Thank you, Michael. It's great to be here. And do residence halls, but I don't think I ever got one to do it. My alma mater. Although if they're listening, we'd be more than willing to submit qualifications for an RFP. I'm going to present biogenic building sections, and in a sense, this work kind of builds out of a book we did about 8 years ago that was in a sense trying to make clear how architects deal with the problem of section, particularly since capital tends to not want section, which is to say that often section is expensive. It's a way of taking away real estate. It goes against kind of certain notions of efficiency, and yet it's often the defining characteristic of a building. And we also wanted to find a way that we could actually develop a kind of language or a kind of framework or a typology, if you will, of sections, so that when we as critics are involved in discussions, hopefully the level of conversation of the crit would rise above simply saying, you have a good section or you have a bad section, but what qualifies and what differentiates a section? Why do we claim that a particular section is interesting, and why do we claim certain sections are uninteresting? In the process, we explored ways of looking at buildings through a kind of combination of section and perspective. That we really like the fact that it both looked at a kind of abstract cut, something that was invisible, the measurable section through a building, but at the same time also allowed you to inhabit the view through the perspective. So it was both kind of abstract and embedded at the same time. It was painful to do these. It's very time consuming to do these drawings, but it's been I think it's been a fruitful book, and it's been translated into I think 6 or 7 different languages. So we've been really pleased with the impact this manual section has had. I would argue that our more recent book, Manual Biogenic House Sections, as in our argument, would be actually a more important book, in part because we moved into the kind of question of the materials that are used to produce buildings. And particularly in the light of climate crisis, in the light of kind of crisis of toxicity, one way that architects can engage this issue is through the specifics of materials. And so in some respects, we see this as a kind of paradigm shift away from 20th century modernism and its material basis. The book is structured according to 10 different chapters, 9 of which are bio or geogenic based, and the last one is reuse. And I'll start actually with the reuse because in some respects our office has always been involved in reuse. The cliche with reuse is that the most green building is the one that already exists. I think it's a perfectly good cliche, but more importantly, it allows you to do other things. The act of working with an existing building is super interesting. It allows you to take a building that might have been, say, a theater that was then turned into a department store and then now being reused as a contemporary art center, so that the trajectory of the design in effect affects how you go about even engaging with it, right? So here, we looked at these tactical additions that were added to this history. So in a sense, the building is this accumulation of these different histories. We would never design this from the ground up, and that's what makes it interesting, right? It's interesting through its kind of layering. Essentially, this was designed effectively over a period of 130 years. Another project in California, we were asked to look at a maintenance building and convert it into an open office space. We would never develop an office building that would have this kind of column-free space. You just wouldn't do it, right? So, but this was the plumbers area. This was the area for the maintenance workers. This was, in a sense, all the kind of trades that the university used to house on campus that they realized they no longer did because it was cheaper to actually go out and get them from outside of the context of the university. But we were able to take this building, which was only about 10 years old, and reimagine it and take advantage of the fact that it has this column-free structure to deal with this kind of new diaphanous ceiling. We kind of perforated the whole ceiling with skylights so that it essentially had an atmospheric effect. Again, only a product of the fact that it wasn't a ground-up building, but in fact, reusing an existing building. Or a museum in New York, Poster House, which was this through block space. But because it had to be a climate controlled museum, we in a sense had to do a building within a building. This building was over 100 years old, so it was quite porous. There's no way it was going to have the humidity controls we wanted, but we didn't want to lose the quality of the space that was already there. So in a sense, we built a building inside a building. The gallery was controlled. We went through all kinds of diagrams for how we might do that kind of ship in a bottle, and ended up with a kind of much more simple version where we thickened the zone where we wanted the gallery and thickened where the public entry would be, and then started to look at some very simple geometric moves to start to sculpt that form so that we could end up with these two long lines that crossed the full block of the building and intersected precisely at the gallery entry. Opposite this building, within a building, was a very long 230-foot long piece of cabinetry that had to actually slope about 3 feet from 24th Street down to 23rd. And so you end up with a project that almost feels like it has a split screen. On the right-hand side is the new building. This is all clay-based plaster. And then here you have the existing building that this is positioned within it. You still get these kind of interesting transitions over that line. So here the kind of seating, which actually is adjacent to where the coat room would be, kind of transgresses that line, or the cafe is visible on one side. We like the idea that you would still maintain the presence of a kind of promenade or a street, because of posters, natural habitat is the street. So why don't we hold on to that? Let's just keep that there, but still maintain the ability to have a gallery with full humidity controls. The capitals were always super important to us. So even when we wanted to drop the ceiling, we would then kind of sculpt the space for the capitals and illuminate them and almost put them on display in the thickness of the new building that was added inside. A lot of reuse, and frankly, a lot of kind of repurposing of buildings that we've been involved in has to contend with operational carbon. Basically, you have to make the buildings energy efficient. This was a 1960s laboratory at Cornell. And a lot of the work, frankly, went into reskinning it, skinning it in a way that you had proper insulation, high performance, it would be self-shading, all the kind of operational carbon questions that one tended to deal with, and use that to kind of generate some of the form. But one of the downsides of this is that we were not really engaged with the questions of the embodied carbon, or the carbon necessary to build the building in the first place. And that, in a sense, is the kind of prominent or the dominant shift within the practice over the last 5 years. We've been really interested in ways that one could intensify the agency of materials that sequester carbon in particular. And so what I'm going to present is really a kind of mix between these two books. This is research into other people's houses that have worked with bio-based and earth-based materials. And then these are a series of houses that we design using plant-based materials. This is all stuff you should know, so I'm going to go through it quickly. But basically, we're not, the climate problem isn't going away, and our current trajectory is leading to a level of likely catastrophe. The argument, and this is not arguments we've made, but others, whether it's Architecture 2030, AIA 2030, or the Carbon Leadership Forum, and others. But basically, we need to be in a position where we're reducing carbon drastically in 5 years. It's not happening in order to get to net zero by 2050. And everyone's heard this stat that the buildings and the built environment is responsible for about 39 or 40% of global carbon. Of that, a smaller percentage is embodied carbon, but the issue is that the embodied carbon has not been getting as much attention until the last couple of years. Operation carbon has been dominant within the architecture world, and yet if you look at a new building that gets built, about half of the carbon footprint or the carbon emissions from it between now and 2050 are going to be because of the materials up front. And that gets even worse if you're looking at a high performance building, not surprisingly, because the fact that it is so efficient operationally means that even more of the percentage goes to the embodied carbon. And that carbon is bought up front, so it takes a while. It takes, a number of years before that operational carbon is released to the atmosphere. So if we're trying to contend with carbon problems, we have to deal with embodied carbon. There's an argument that has been made that we should stop building, we should just reuse. That's the best way to move forward. The problem is it doesn't deal with the fact that there's global demand that's pretty extreme for building, so we can't reuse our way into the future. There has to be a model that looks at building, but building in a way that has a better relationship to the environment. And in particular, this means that there's going to be a paradigm shift. And this is what frankly gets us fairly excited. That in a sense, whether we want to admit it or not, we're still living in the legacy of modernism, legacy of carbon, steel, and glass. Carbon intensive, the idea that everything can be global, that architects are ultimately kind of positioned as consumers. We specify products, right? And we're very excited by the prospect that architects can essentially work much more as kind of engaged participants in larger life cycles around the materials, and that these materials are predominantly plant and earth-based. They're low carbon, they're local, they're renewable, we're concerned about their cycle. We're not just kind of specifying and then using and getting rid of materials. And we know that not all materials are equal. So on the upper level, to the right is the carbon intensive materials, the glass, steel, concrete, and everything that sequesters carbon, not surprisingly, uses photosynthesis, plant-based on the lower left. So how do we use this as a basis for design? In other words, the purpose of the book was to make legible buildings, and in particular houses that have used plant-based and earth-based materials as being generative within the architecture, not positioning them as substitutions for existing, materials, but actually as generative for the very thinking of the building. So one of the keys for us within this book is that there were 55 houses selected from around the world, and each of them had to have a level of architectural invention. There had to be a level of seduction. In other words, it's not simply about working with these materials and building banal buildings, but in fact, what are the possibilities that are released by these materials? And more importantly, making sure that that seduction, which is one of the key things we bring to the whole dialogue about the built environment, that seduction is still at play, and it's germane and relevant to the very materials that are being engaged. One of the critiques of the book that we have is that we shouldn't be doing houses, and we totally get that, right? One should be looking at housing, not houses, and that's acknowledged up front. One of the reasons why we dealt with houses is, one, that the scale of the house section was sufficient that in the format of a book, you could actually read the materials. So that was key. The second is that there are not, when we wrote the book, there were not a lot of housing projects that use these materials. That's been changing, but it was very difficult for us to find, say, a straw bale or a straw-based housing project, let alone 5 of them. So, but we could find houses. So houses, which have always been the site of architectural experiments, have continued to be that way. And so we were able to capitalize on the fact that we could find built examples of all of these materials with multiple examples in the form of houses. I should say that all of the houses within the book are small, most are less than 1,000 square feet, which is important, and they all have inventive sections and an architectural ambition. Okay. The book starts with a critique of the overscale American single-family house, not just kind of tracking its carbon and where it comes from, but also just making clear that this building has gotten quite big because of the cheapness of the materials, the petrochemical materials that are used to make it. Houses used to be about 1,000 square feet in 1950. They're now 2,500 square feet. And that's made possible because all of these materials are essentially very inexpensive. So you can build a larger house because you can get materials that are quite cheap. But these materials are not great, and they, I won't go into them at length. Others have done that. Parsons Healthy Materials Lab has a great resource on the health of building materials. But these tend to be materials that have a limited lifespan. They tend to be toxic. They're sites of fabrication. They tend to off-gas when they're in the buildings. And at the end of life, they lead to essentially landfill. And those lives are not at the point where they've exhausted their usefulness, but they've tended to no longer be fashionable or no longer be economically the right scale of building for a particular site. So demolition occurs not because a building has deteriorated, but because it's no longer valued. And at the end, of course, we get excessive landfill. So there's a kind of crisis of carbon, but there's also a crisis of toxicity that are combined here. The other thing that is kind of very useful for architects to think about is that when we get obsessed with buildings, we tend to care about structure, and we care about the interior finish and the exterior finish, and there's not as much attention paid to what else goes on within that wall. And what takes place within that wall is pretty astounding. There are multiple layers at play here. Anyone who's specified and developed the wall section starts to realize there's anywhere from 6 to 15 different layers. They tend to be all pretty lightweight. They're thin. They're usually single performing. There's lots of them. And they often set up this very strict binary between the exterior and the interior. And to be honest, architects don't tend to engage in the full depth as a design issue, right? We tend to mostly care about what it looks like on the inside and the outside, and maybe the shape and form that it takes, and perhaps its performance criteria. But how we get there is not as much on our radar as it should be. On the other hand, what we look at within the book is the possibility of thicker walls, of single performing walls, of walls that might be made out of a single material that does multiple things. And in a sense, embracing things that were rejected by modernism, say thickness, for example, or the idea that something might have to be maintained. Every building has to be maintained, but somehow we're deluded into thinking that we're making a maintenance-free building. So bringing in maintenance as a kind of necessary component to the project, and really kind of rethinking the very material palette of what we work with. So I'm going to present these in sequence, going through some of the examples. Within the book, what we do is we always present the material, we present the kind of carbon associated with it based on publicly available databases. There's very little that can be super precise about carbon. It's an abstraction, it's a rough guide, and that's another whole problem, the whole number counting, but there is a kind of relative scale, and so we wanted to kind of give a rough range of where these materials fall. We follow that page with a page that looks at the life cycle of the material from its growth to its use in buildings to its end of life and how it can be developed into a circular model. And then the next page looks specifically at how one goes from a plant to a useful building member, if you will, and the transitions, the key steps in that transition. So in a sense, how does one translate from the field to a kind of form, if you will? There are usually about 5 or 6 examples of houses within each chapter. Within each of those, we wanted to feature not only the exterior view and the interior. Not many of these are canonical. In fact, very few are well known, which is actually really nice. Most of them are actually from the last 10, 15 years. We wanted to make sure there was an example of it, the project under construction, as well as our custom drawn cross-sectional axons to reveal the floor plans. And then the next page has the cross-section perspective that allows you to see how it was made, the scale of the members. We try to think of this as a kind of a visual scholarship where we try to be as precise as possible with all of these materials and how they come together and the spatial qualities that come across from the project. As I mentioned, after 5 years of doing this, maybe more like 3.5 years of doing the book. And I should mention Adam Ainsley was instrumental in the start of the book. And it took a while, and we realized that we actually wanted to design our own houses. So we ended up developing about 5 houses that were our take on if you could develop innovative architecture with these materials, where would you go? So I'll present some of those as well. I should mention that Kyle Reich, who works at LTL now, helped install the exhibition. He was instrumental in doing this book, as was Celia Chesabel. So the two of them, there were many people involved, but the two of them in particular played a heavy role in advancing these projects. So a shout out to both of them, particularly Kyle for making the exhibition come together. Okay, so these houses usually involve a couple of different projects, different materials. We don't see materials operating in isolation. It's often the hybrid that becomes interesting. All right. So mass timber. Mass timber is the kind of poster child for plant-based materials. It's much more advanced than many of the other materials I'll be talking about in terms of manufacture, code, acceptance from contractors, et cetera. But it's not going to save us. And let's be clear about this. Mass timber has its problems, right? It's better than steel and concrete, but in general, the question about its greater benefit is still not fully resolved. And what I mean by that is that if you look at how long it takes for a tree to grow, the disturbance of the soil, even if you're looking at good forest stewardship, you still are maybe not getting a net gain by the sequestering of the carbon because of the loss of carbon to the soil and to all the parts of the tree that don't get used within the building. So if only half of the tree gets utilized for mass timber, you have the other half that, unless it's properly incorporated, is going to basically biodegrade. So you're left with basically a wash, right? And so mass timber has some problems. The downside I've witnessed in schools of architecture is with Rhino models where you used to ask a student, hey, what did you make your Rhino? What is this made out of? The response is usually, it's concrete and glass. I'm like, okay, concrete and glass. Now, if you ask a student what their project is made out of, they'll say it's cross-laminated timber. I was like, okay. So there's this weird way in which it's simply a kind of substitution into the generic world of Rhino. And that's a bit of a problem. So, okay. The other issue with mass timber is the glues. Despite claims of bio-based adhesives, they're not dominant. We're still looking at mostly plastics as adhesives. Things like nail laminated and dow laminated timber have a lot of interest, super interesting what those might do, but they're still less dominant within the mass timber world as compared to cross-laminated timber. All right. The other thing, and I kind of hinted at with my critique of the role of rhino, is that often mass timber is simply replacing, in the construction world, is simply replacing a slab and beam approach, and that seems to be a missed opportunity. And one of the things we tried to use as a criteria for the book was what houses are really using mass timber in ways that are specific to the opportunities made available by mass timber. So Jennifer Bonner's house, Gables, is clearly only possible because of the unique tectonic and structural capacity of this millable sheet good to form these complex kind of roof lines that would be very difficult to do with just simply a whole series of smaller 2x. Or the Meteorite by Atelier Satma is in a sense just 2 layers of mass timber. The faceted form is a product of being able to mill mass timber at a high level of precision that you see down here. And as you can see in this section, the project is just 2 layers of CLT. An interior layer forming a kind of rectilinear inhabitable space, and outside a kind of faceted outside, and then these very large interstitial spaces between, which are effectively an insulation layer. There is no insulation, there's no cladding, there is no interior finish except the CLT, and the only cladding on here is a black stain that's added to the outside of the mass timber. So it's really interesting to imagine how you could start reducing some of these other layers by pushing mass timber to do more than it would if it was simply replacing the stud wall. The other thing you start to get is a fairly high amount of carbon sequestration, 48,000 kilograms of CO2 equivalent. All right. So with a house that we called the kind of CLT A-frame, we were interested in what would happen if you didn't actually cut a CLT blank into all kinds of different pieces, but actually use the entire thing. What happens if you took these very, very large pieces of material, 10 feet wide by 50 feet high, and actually just let those be the generator of the geometry for a house. So our strategy was to say, okay, at the back of the house, let's let these things be parallel to each other, stand upright. They'd be supported by the stair that would kind of stiffen that back portion. And as you move to the front of the house, these panels simply kind of tip toward each other, forming this extremely high building, 50 feet high to the top of the wall. And that also allows you to start to inhabit the space of that kind of roof deck up within the trees of this house anticipated for the Pacific Northwest. On the inside, of course, you get CLT as the finish, and cantilevering into this very kind of unique kind of proportion section would be the sleeping lofts and the other rooms. So everything takes place within the space made as a product of the geometry of the CLT blank. Okay. Bamboo, unlike mass timber, is incredibly fast growing. Bamboo tends to be harvested after about 5 years of growth. It has greater capacity, both in terms of tensile and compression strength than wood, and it starts to rival actually concrete. It grows extremely fast, and one of the nice things about bamboo is that it is not clear cut. You basically go in and remove 1/5 of your bamboo forest at any given time because it's a 5-year growth cycle. It constantly regenerates itself. You're not disturbing the soils. You're not disturbing the roots, and essentially it's constantly being cultivated. The downside to bamboo is that you often have to cut it up and re-glue it into all kinds of different smaller pieces, so the adhesives become a real kind of problem. Although one interesting thing is to look at how the culm itself could be used as the kind of point of departure. You get into the issue of non-standard, right? So the 2x4 is a great way to standardize construction. So a kind of natural material could be seen as being consistent. Culms are all unique, but there are ways to assemble them that take advantage of their density and bundling them to produce things that are more self-similar, beams or columns. So this particular house actually used the culms to cross-brace the house through a series of then ramps. So in a sense, the house has no stairs, it just has a continuous surface moving up it. We really like the fact that the structural stabilization of the culms actually generates a very different inhabitable space for a house. Or in a project by Anna Herringer, here the flexibility of the bamboo allows for a really unprecedented kind of exterior skin, providing a kind of loose atmospheric effect around the rammed earth and interior. This is a youth hostel. It really kind of an extraordinary building that is only made possible by, again, the flexibility of the individual bamboo columns. All right, shifting to earth. This certainly lacks some of the capacity to work in tension, but it's incredibly good in compression. It's been around for a very, very long time. Often when one thinks about earth construction and rammed earth, it uses a fair amount of Portland cement. So one of the questions here is, can we still work with clays as the binder? One of the fascinating things about working with earth is that it can actually be a liquid that then gets translated into a kind of form. So the ability to kind of print it becomes really interesting. And just a couple of the examples, this is a house that actually combines earth and straw to make a kind of cob wall. This is about 32 inches thick, and as you can see here, was placed as a kind of mass on the wall, and then simply carved with a shovel. And you get this really interesting contrast between the roughness of this earth wall and then the wood ceilings and floors. The floors themselves are filled up with straws and insulation with large projecting eaves to protect the earth from erosion. And in the kind of tectonic detail, you can see that the earth is actually not load bearing in this case. It's simply the interior finish. It's the exterior. It's the insulation. And it forms the kind of enclosure for the building. It absorbs humidity and releases it. It dries itself out. And the fact that it has a fairly tall foundation and the overhang keeps it from being damaged by water. Kind of an amazing house that just simply uses the mass of the cob wall. A different model that's built into a series of blocks. These are earthen bricks, 4 inch by 6 inch by 16 inches in Burkina Faso by Carré Architecture. And I think there's something like 12,000 bricks that were made on site, and they were used to form both the walls, but then also these simple arches that then were protected by a small amount of metal, right? Reusable corrugated metal that ultimately channels the water to the tops of these walls. And that really starts to form the geometry of how this stuff is all linked together, essentially using the building to harvest water and place it in an underground cistern. Really interesting project, fairly simple, but the cumulative effect is pretty impressive. As I mentioned, you can 3D print earth, and this is a project outside of Bologna where half-inch layers of earth. This is not, there's no Portland cement added to it. It's simply a clay-based earth. Producing roughly 30-inch thick walls that were open and filled with rice husks for insulation. Really interesting project that imagines the possibility of 3D printing without having to resort to a lot more concrete. So with the Lamella Earth House, we were interested in how you could take kind of bamboo and the efficiency of it, the structural capacity of bamboo, and develop a kind of lamella structure using 8-foot lengths of bamboo, and then inside that larger scale volume place a series of, or a kind of earthen structure. So the lamella structure is really taking the same 8-foot units and a single detail and basically expanding it out so it forms a continuous kind of dome, if you will, or extruded arch. One side of this was then clad in thatch, and the other side with a kind of translucent plant-based polycarbonate, which really gives you a greenhouse, so a kind of interstitial layer between the outside and the inside, being able to use for kind of plants as seasons permit. But more importantly, provides a buffer zone to the extremes of the outside climate for then what would be the inhabitable interior, which is made out of the very soil in which the house is embedded. So in a sense, you get a house that's inside of another volume. This volume is kind of playing the role of the barn, but you still get the house within the barn, if you will. And we like the idea that one could start to imagine different models, and in this case, a kind of farm-based building type hybridized to start to move into the world of the domestic. Okay, so The next three materials I'm going to talk about to conclude the lecture are all insulation. And I know very few studios start with insulation as their point of departure. It just isn't where you go. But it is amazing stuff, right? And it's also the source of a lot of carbon. And frankly, a lot of petrochemical installations are on the market. Most installations burn horribly. So if you ever want to have some fun with XPS, just try to set it on fire. It's going to go up. It's going to leave incredibly toxic residue in its smoke. It's just really nasty stuff. It's high performing, no question, in terms of its resistance to heat movement, but most petrochemical based installations are pretty unpleasant. And if you've ever installed fiberglass insulation, you know what I'm talking about. It's not like any material you have to wear a hazmat suit to install it should be a warning sign that maybe this isn't the right material for what we're doing. Okay, so hemp is a fantastic plant. It grows super quickly. It can be harvested sometimes twice in a year, depending on the growing cycle, so about 2 to 4 months. It tends to require very little water, no fertilizer, limited amount of, if no pesticides. It often rejuvenates the soil. The use of hemp has been limited by its association with the psychoactive THC, which is a different species of hemp. But because of the war on drugs, basically hemp was eliminated from the US until around 2018 or 2016, the Farm Bill that came through that made it legal to actually grow industrial hemp again. Hemp itself has to be decorticated, so you have to separate the fibrous exterior shell from the inside hurd or shiv. The shiv actually works very well as an insulation because it has a cellular structure that captures a lot of air, whereas the fiber can be used for fabric, paper, and frankly, it could also be used for a bat-based insulation. It can be kind of formed into a wall on site, kind of combined with lime, can be used to kind of make blocks or be used directly in a project. There's a term hempcrete that refers to the combination of lime and hemp. It's not the best term because it suggests that it has concrete-like capabilities. It doesn't. It is insulation. It is not structural, but it is resistant to rot, to insects, to fire, et cetera, and performs extremely well. I love cork, but cork is not scalable. That's the biggest problem with cork. There's only so many places in the world you can grow cork. It takes a long time for the trees to grow, and it takes another period of 10, 15 years before you can harvest the cork off the tree. It is an amazing material. It is able to work as a cladding. It's able to be structural. It's insulative. It smells great. It works acoustically. It's a fantastic material. It's just very hard to scale it because it tends to only grow in Spain and Portugal, and often it's as it's used in architecture, it's the residue of the cork wine stopper industry. There's initiatives to try to recycle more wine bottle stoppers as to turn them into architecture, which may increase the quantity of cork available, but still we're limited. Like you can't scale that much with it. That being said, just to show an example of an incredible house built almost exclusively with cork, there's a cork house built with 1,268 CNC milled blocks. It's the insulation, it's the interior finish, it's the exterior finish, it's the structure, it does everything, right? And it's corbelled up to produce the enclosure. There is a wood ring beam that runs around to help stabilize the blocks together, but it's effectively an all cork house and is really quite beautiful in its own right. Okay, but there is one material that is scalable, that is available everywhere in the world. The amount of carbon stored in straw, some argue to be equivalent to the carbon released by the concrete industry or by the country of India. So there's a massive amount of carbon being stored every year just in the agricultural waste of the cereal grain industry. So we're talking about wheat, barley, rye, et cetera. The stalks, after you take away the seed where you get the flour and the cereal grain, the stalks that are left, which have very limited, if no nutritional value, that material sequesters a massive amount of carbon globally. And the question is, how do we reuse it? How do we actually store it into buildings rather than extracting carbon through carbon sequestering technologies that bury carbon into caves through multi-million-dollar ventures? We have something that's actually doing that. The question is, how do we actually use it better in our buildings? Straw has a long history of being used. Actually, I shouldn't say a long history, a short history, but long in the terms of the United States, because it's been around since the 1800s, late 1800s in Nebraska. Straw bales were used to build buildings. Typically, you're looking at the need to work with a baling system that is really not designed for architecture. It's designed to get the stalks off the field. So it's actually a very bad building product because it is talk about non-standard. Like, these bales are going to be not contingent upon how they're being used architecturally. They're about the machine to get them off the field. You can use straw within the context of a wall, whether it's kind of placed within an existing frame, or it can be stacked up and be load-bearing using the plaster as your structural skin, reinforcing and really carrying the load. Or you can look at putting it into a prefabricated assembly. Again, the interest in straw is how it can also be structure and insulation simultaneously. And there's also the possibility of thatch, which is underdeveloped in this country in particular. Just a couple of examples. This is an amazing project that used jumbo straw bales. These are 30-inch by 60-inch by, I think, 150 inches. They weighed each about 700 pounds. These bales were stacked up and form similar to the cork house, if you will, in geometry. It's basically nothing but straw. It's the load-bearing surface. It's the insulation. It has a skim coat of plaster on the inside and the outside to protect it against insects and moisture, but is otherwise a completely straw-based building. And it sequesters a massive amount of carbon, something like 488,000 kilograms of CO2, or 80,000 kilograms of CO2, 48 kilograms per meter squared. All right. So we were really interested in this idea of thickness and how much straw could you actually use in a wall? Could we actually make our walls so thick that they could actually become the rooms themselves? So this project said, all right, could we take CLT as a way to make a kind of frame or a box and do those as a kind of prefabricated unit and insert those into the voids left within what otherwise would be a solid mass of straw? So in a sense, you would get these CLT units being dropped into the voids left from removing some of these straw bales. There'd be a wide kind of horizontally expanding cantilever roof to protect the plaster skin from erosion and from moisture, and a central skylight with a retractable louver to bring light down into the thickness of the building. But really the project was this, the idea that you start to embed your rooms into the walls, right? So that you start to kind of have a Lowsian space that would unfold, spiral up through the project, but basically linking from room to room, with this incredibly thick wall now working its way into the building. We really like the fact that one could start to have a window in a room be synthetic. This really was as porous as possible, but also super thick, and sequesters a massive amount of straw in the process. A second straw house looked at two different ways to use straw. Again, trying to use thickness as a benefit and not simply be something that's criticized. So here we developed kind of two areas for straw. One was a kind of a wall that would follow the topography of the site that would slightly kind of pull away as it hit the house. The other was this thickness of straw, similar to the previous house I showed, with the rooms carved out from in it. But these two then would be linked through a series of structural timber panels that were also filled with straw that would tie these two systems together. The straw would then be clad with a membrane and more straw being put on top so it could be kind of blend into the site itself. There's often a kind of question, won't animals eat your building? Animals don't like straw. It's not hay. Hay is a vegetable. Straw has little to no nutrients. But we like the idea that, yes, if an animal wanted to eat our building, that would be okay. We just build build it into the logic of the project. And then you'd end up with the bedrooms, places where you need privacy, actually carved into the thickness of the straw, whereas the social space is really kind of set out in between these two straw masses. So you get the kind of public space, the dining room, the kitchen, the living room, and then forming a set of steps that allows you then access into the private rooms, the bathrooms and the bedrooms carved back. And most importantly, this thing was mostly solid, right? This is a house that's more mass than it is space, and it sequesters a massive amount of carbon as a result. We also really like the idea you have these incredibly separate acoustic rooms that might have skylights, and again, the ability for animals to start to become part of the house as drawn in the section. Okay. A couple more experiments with straw that we've been working on the last couple of years. One is what would happen if we started working with these more ubiquitous jumbo straw bales? They're relatively inexpensive. I think they're about $60 each. So if they're $60 per bale and you started to just stack 3 of them up, you could get about 12 to 14 foot high wall. You're getting your insulation, your structure, most of your enclosure at about $10,000. If this is 75 by 75, that's 5,600 square feet. It's $1.75 per square foot. So the idea that you could, granted you're not getting your floors yet, but you're getting walls relatively inexpensively has some appeal, but more intriguing from an architectural standpoint is what happens when this starts to be a different way to imagine how you could think about the building. Rather than just positioning your straw bale around the periphery, what happens is you start looking at different ways to carve the space. That the exterior and the interior could be fundamentally different. We could design through removal as much as we do through addition. The thickness and difference within the architectural poche could now become part of the argument without incurring huge amounts of expense, and in the process sequestering a large amount of straw. Becomes really interesting to think how this abundance of straw could be useful here, combined with CLT floor systems, how one could start to design through removal, just simply a kind of diagram of what the architectural possibilities might be. And the cladding is not that complicated, right? One can look at a membrane and then a rain screen on the outside and a kind of cladding on the inside and a CLT ring beam at the top and the bottom. These bales, even though they're round, by the time you squish them together, you're going to get a minimum of 30 inches of straw, which gives you an R value of roughly 50, which is not bad. So our question was then, all right, can we look at an existing building we built and rethink it as a straw bale structure? So this was an early childhood education building in Bentonville, Arkansas, about 40,000 square feet, 240 students, very young age to age 5. They were each organized in classrooms that then worked connected to an outside space or play space that was relevant to the age group. So the older kids would be here and the younger kids would be here. So each of these 6 classrooms or 7 classrooms would all have a collective play space. There would always be this large exterior porch for every one of the classrooms. So even if it rains, you can go outside. And then the interior was framed by this felt roof. For us, what made this project interesting was that it had no plastics. There was no latex paint. It was all mineral-based paint. This is a collaboration with Parsons Healthy Materials Lab. There were no plastic toys. There was no grout. In a sense, we got rid of any no VOCs within the project at all. But it was made out of conventional materials, drywall, metal studs, et cetera. We tried to do a lot with the drywall. We tried to carve it into these kind of sculptural spaces. It was $180 a square foot, so not an expensive building. And so we wanted to return to this to say, all right, what would happen if you imagined it now being built out of jumbo straw bales? Tectonically, it became really interesting. We could imagine the classrooms in this case being framed by these straw bales with a reciprocal frame roof, a wood roof that would form a skylight in the middle. So we'd get each of the classrooms would form these circles. The walls were sufficiently thick that you could start to carve out play spaces within the walls themselves. You could get the bales to go outside and actually become part of the landscape. The play spaces out here. And the working with CLT, we could get prefabricated bathrooms in between each of the classrooms. And in a sense, we would get this project that would almost kind of allow us to keep the similar argument about self-similar age groups having play spaces, but then coordinating into a collective. It was not our intention to make heart-shaped plan. It just happened. That's what happens when you start following the material logic. You end up with forms that are Instagrammable, which is great. And just to be clear, this was our round bale version. We did the same thing with rectilinear bales, and not surprisingly, we ended up with a much more rectilinear project. Similar argument in terms of program. Okay. So the last thing I want to present is some experiments that we've been working on in trying to develop a structural installation using straw. And the real problem here is binder. The argument is that if you can compress straw sufficiently, it can actually be load bearing in a way that regular straw bales aren't. Most straw bales are compressed to about, I don't know, 80 to 100 kilograms per meter cube. We were trying to get closer to double that, like 180 kilograms per meter cube. So it could actually be a load-bearing installation, which is kind of the holy grail, right? There are a lot of products available. Some of them are amazing, Eco Cocoon or Croft out of Maine. These are available straw panel systems that are using double stud 2x to make roughly 8 foot high by, say, 40-inch wide and roughly 12 to 14-inch deep that use straw, whether it's compressed straw or straw bales, as the insulation, but it doesn't deal with the problem of structural straw and lets the wood play that role, which makes sense in terms of getting it into code, getting contractors to build with it, et cetera. And even new frameworks out of Vermont will actually teach you how to do this. They have a program to mentor other contractors to make straw panel systems. They have a whole kind of class set up to make this possible. The idea of developing a whole series of locally based straw panel companies is great. So we're all completely supportive of this. In fact, we're using one of these products in a project we're building this summer. That being said, we were really interested in could we actually work with binders and compression to get straw to hold to itself to make a form that would do that. So the binder was key. So how could we work with earth or limes or mycelium? We invented a compression machine inspired by Croft out of Maine to try to compress straw to get the density that we wanted. We were kind of making a whole series of these test blocks. There's about 24,000 pounds of force being used to compress the straw into these molds. One of the problems is it takes a while for these things to dry, so the molds had to be kind of openable, unbox them. We had our units, and then we kind of ran them on a series of compression machines. We also found it's enjoyable to give straw a haircut. It makes a beautiful surface, by the way, so really gorgeous. That's the compression level that we were able to get with a kind of SIP system. But to be able to then test these, we cut them up and then place them in an Instron machine at Princeton. And you can see it has no deformation horizontally, and it bounces back. It's able to take on increasing loads, but the downside is it's still super squishy. We also looked at thermally testing this to see what R values we could get. And to be honest, the answers we've been getting are not, they're too good. So this was some experiments we did in 2023. Go through these a little more slowly, the compression machine, the straw being compressed into these volumes. Trying to work with different binders. A couple of things just to note is that some binders form their own skin so that they don't dry out on the inside. So if you use a wood glue, which is not great to begin with, but it'll form a skin so that the inside doesn't dry. So it rots. So that's a problem. Mycelium was a disaster, even though I would love it to work, mostly because it's so dense, it doesn't grow into the depth of it. So it only forms a kind of shell of mycelium around the outer inch within the compression system. Here are some examples of the mycelium. Our most success came with lime, and lime is not great, right? And it's not a lot of fun to work with. And So we've struggled to get a perfect solution from these particular binders. To be honest, we're kind of more interested in possibly getting rid of binders altogether and developing a SIP, or a structurally insulated panel, where the straw is compressed inside skins, whether they're plywood or OSB, and they may be stitched across to each other to form a kind of stable unit where the straw would still play a structural role. And again, I think that the difficulty of the kind of rebound, we still need to find a way to get that compression to really hold. It's not quite there yet. And the R value, the biggest problem here is that when we set up the sensor, the straw is very hard to get a proper read on the surface of the straw. Even if we embed the sensor in the middle of the straw, have heat on the insides, and we bring it to a steady state, we're getting R values that are just too good to be true, right? It can't be R6 per inch. And I think it's because it's moving around the sensor in a way that's not getting a proper setup. So we're looking at other models to test this. That being said, the exhibition is an opportunity for us to kind of present some of this material in different format. Just by way of explanation, the exhibition really has three components. On the outside of the exhibition, we've, in a sense, unfolded the book into the space of the gallery. So each of these stands holds one book open to a particular project, with then other images of that project placed above. So in a sense, we like the idea that the book and the exhibition kind of become one and the same. On the inside, we've located a series of materials that go from most carbon sequestering on this side of the circle, or the amoeba, to the most carbon emitting over here. And the rough quantity of carbon is identified on the plaques there. And then the third component is the series of projects, some of which I've been describing, that exist on the wall. And so I will say that we're particularly energized by the agency that different materials bring to architects. It allows us to do different things. It's not going to be easy, but it's super fascinating, and frankly, it's the right way forward. And in a sense, it can be a kind of paradigm shift for a different model of architecture that hopefully all of you will engage in. So thank you very much.
Great. Thank you so much, Paul. The good thing about being the guy with the mic for Q&A is I get to ask the first question if I choose, and I do choose. Thanks so much for that. I want to ask a question specifically about the relationship of these materials and the sites where they are harvested. Because the book is so detailed in how these materials come together, and the question of, as you said, the kind of generative capacity of the material to create architecture, and the kind of the cycles of materiality. It kind of makes gesture to forests and fields where stuff is harvested, right? But then there's the question of, well, what are these actual places where these materials are harvested, right? And we see, in the discipline, we see writing by Kiel Mo, working on construction ecologies, looking at his book Unless, looking at the Seagram building and the kind of ethnography of where all this material is coming from, coalescing into a skyscraper. In the landscape side, we have Jane Hutton looking at what she calls reciprocal landscapes, the relationship of built projects and the sites that are where the materials, the quarries and everything else where things are harvested. So this morning, you and I had coffee, and you were telling me about harvesting Phragmites and harvesting from a particular place in the world, that there might be a grant or an opportunity to kind of, change the landscape over here and create architecture over there. And I'm really interested in whether or not that is an idea that's kind of promising to LTL, to the practice. Is this the start of a real investigation to that question?
Yeah, I mean, I think the bigger opportunity is that if one doesn't think about materials inherently being globally available at all times, everywhere for everyone, but starts to take consideration of where things came from. And in particular, when that isn't just a punitive, oh, you need to source, you need to track where this came from, but really more, it's actually better for it to be local, right? That idea that what we get involved in is not simply picking products that are on the global market, but actually able to identify fabricators who are sourcing the materials locally because it's simply better and cheaper. And frankly, there's greater control over sourcing it locally. So a good example of that is if you look at straw panel fabricators, they don't want to source their straw from California and have it shipped across the country. They want to be able to talk with the farmer who they're going to get the straw from because they know that they can talk about when their harvests are. They know when they're going to get it. They can reduce their transportation costs and developing that relationship allows much greater control, quality control, decreases costs, and also, frankly, brings the thing much more within the realm of a fully curated product. What we've been looking at with Phragmites is trying to figure out ways that we could use materials that are ubiquitous, but would have to be sourced locally. And one of the interesting things we've gotten into is that in order to harvest Phragmites, you have to get into the fact that it's an invasive species. So you'd have to deal with it in a way attendant to that problem. In other words, you don't want to harvest it with the seed heads on it, put it in a truck and transport it a couple of states away because you're basically spreading Phragmites as a result. So there's strategies of harvesting it, cutting off the heads, leaving it in the field, working with the stalks. Frankly, there's no point to sourcing it from other places in the world because why bother? If it's available here, get it here, right? I think that part of what starts all of this is simply a kind of an interest and a knowledge. And to be honest, our architecture world has not been that interested in really where the materials came from as long as they were inexpensive and performed at a certain level. I think being able to be more precise about where they're coming from, taking an interest, making that part of the project simply makes things more enjoyable at some level. So, there are a number of different examples I could go through, but I do think that there's that engaging design and assuming that thinking about the materials goes beyond simply how they exist as a product, but where they came from, it just opens up the arena in which we can be beneficial. So.
Yeah, you showed me a picture of you standing in a field of Phragmites where you spent half an hour kind of cutting and harvesting, right? So you changed that place and you're going to be changing another place by taking that material somewhere else and building architecture, right? So now those two places in the world are in relationship to each other in a way that they weren't before. I think that's really kind of fascinating. Yeah. I think you're right about it gets away from the anonymity of kind of sourcing materials from God knows where. Yeah. Who cares, right? Yeah. Actually, it's really rich to think about where it did come from. Yeah. Thanks. Great. Who's got a question? Iman, I saw you first.
Iman, click it on.
Hi. Hello. It's working. So I guess moving from the site and the sourcing to the actual construction. You mentioned that like thatching, for example, is not super well developed in the States. And so I guess I would like to know your thoughts on how a lot of the use and construction of these materials can start to invade the construction landscape in different regions where these materials are not used, but also how that, if you've thought of that as a potential way of like more ethically developing skills and trades, and using that as an opportunity to, I guess, address labor issues and labor concerns in different areas where there's job shortages or other things like that.
Yeah. No, it's one way to think about it is that, like, if you take straw and rice harvesting, for example, doesn't tend to value the straw, and there's all kinds of kind of rice plant fields and areas that have been planted in the South. And if there's a way to take that rice straw and actually make it have value because it can now become part of a building industry, that adds value to a place that didn't have it before. So there's certainly that, right? I think that I mean, you're getting into a world that I mean, architects are kind of perpetual amateurs at all kinds of things. So I'm a little worried about getting to the realm of knowing too much about labor because I'm not a labor specialist. But I would argue that one of the interesting trajectories that we have to follow is how do we shift from things that are very intensive manual labor, and thatching is a great example. Frankly, straw bale construction is super labor intensive. A lot of plant-based material construction is fairly labor intensive. And that I'm not putting forward as the future. And in some ways, that's its current state. The interest is going to be see how those materials can start to be translated into a form of construction or a form of product that benefits from the fact that it can be locally harvested, but is ultimately it is going to be a product, right? But it's being sourced from plant-based. So a good example is timber HP insulation in Maine. And they've taken advantage of the fact that the lumber industry in Maine, which used to make a lot of paper products are not as in demand for the newspaper industry. So they have a lot of this residue from the timber industry, the stuff that doesn't get used to make lumber that's backing up. And they've realized that they could actually give value to that by using it to make wood fiber insulation. So that technology is coming from Europe, being brought over, but they're investing in a very large plant, and you can buy timber HP wood-based insulation that then enables the forest industry to have a value source that it didn't. But it's not done through labor-intensive hand. You know, it's millions of dollars of machinery to make this stuff. So I think it would be a mistake to assume that we're all going to go as architects and make our own thatch. As much as I enjoyed going out to the field to harvesting Phragmites more, so I have a sense of what it is, but I don't imagine my future is to be making thatch. I think it would be a mistake to assume that somehow we're going to return to a crafts technique where architects are also kind of crafting things. That may happen, and that's fine, but I think it's like how do these materials work their way through a more industrialized system? And how do we kind of push that from our standpoint by demanding them? And at some point, you may have to start with a more manual-based one, but we may end up with a version of thatch that's actually highly machined, maybe not highly processed, but at least run through equipment that can reduce the cost of it significantly, in part because it's going to reduce the amount of labor that's necessary to install it. So it's a really good question, though. Yes.
One of the challenges of like construction in general is like managing water and like water membranes, and there's a lot of thermoplastics within said material. And I was wondering, like, you're looking at thickness of straw, and that might be a way of managing water. But how did you think of water? Like, did you think of water as like a material or as a formal generator?
That's a good question. No, I mean, I would point to, the Burkina Faso project where the roof was used to harvest water. And certainly the use of harvesting water is crucial. It's not something that we've directly engaged. I think that moves into a kind of different, I mean, it's not uninteresting and it's not unrelated, but it's not something that we use directly in any of these particular projects. Although there are examples of them in the book where water and the harvesting of it was key. Because once you start looking at everything as a resource, you can't ignore that, right? So, and that also leads to other issues that thatch roofs, for example, are not great for harvesting water because it may turn out to be that certain, metal roofs might be better than, others for if you're going to use it as a potable source. And so it becomes really interesting, like how all these things start to affect each other. So.
Thank you so much for the lecture today, but also making this resource, these books, that I think are, it's wonderful to have access to this. So you're normalizing and spreading the conversation. I wanted to pick up on the first question, which was about It's really about maybe like access.
Mm.
And I've noticed it's interesting with some of these products that to scale them, to even manufacture them and use them more generally in buildings that aren't just houses, we're moving towards like, how do you develop code language, right? Like how do you test them? What's their insulation value? And it's interesting because usually the code language is funded by people who are patenting some of these technologies, right? And that leads to this phenomenon of like, in some ways, closing down the access. Like in one sense, you get the code language so everyone can build with these materials. But in the other sense, the code language means that certain companies are now patenting what really is traditional design, right? What really are these techniques that, people have developed over centuries. And I think there's an interest in seeing these technologies remain open access. Seeing these technologies also accessible in terms of just, small scale contractors being able to build with these products and compete. So I'm curious about, what your perspective is on, for example, like what does it mean to test cob and get cob into the building codes? And what does that mean in terms of access?
Yeah, it's a good question. I don't know if I have really good answers to that. I mean, I do. Maybe my best answer is to use the example of New Frameworks out of Vermont, who's done amazing work. And they, for many years, were working with straw bale as the construction. And I think in a weird, in a very direct way, they've shifted to a panel system because it can be prefabricated offsite, but also because the wood system is accepted by code and it doesn't produce any resistance, right? What's interesting about this is that they're able to develop a kind of 2x framing system, but ultimately it's a straw bale system in terms of its majority of its carbon, right? What they've done beyond that is recognize that because these things get to be pretty heavy, you don't want to be shipping them across the country, right? So they're keeping their region very limited and then teaching other people how to build. And I think that is a great example. They're committed to open source. They want competitors around the country, right? And that I think is a very different model. They're probably the exception to the rule. Their interest isn't like, controlling the market, right? But it's what you're getting into is a really complicated issue, which is that in order for these materials to scale, for us to shift away from concrete, glass, and steel and move into these, it is going to involve investment from industry. It can't scale at a DIY level. I mean, or if it can, it's only going to go so far. And I think that's where you're going to get more acceptance of code because they have the money to do it. I mean, it's interesting that even if you look for things like an EPD from a lot of bio-based companies, they don't have them because they cost $15,000 to $20,000 to make. So why would you, as a bio-based company, invest that amount of money when people aren't even demanding it? And so the people who can make the EPDs are the big corporations. I mean, so it's a very complicated world. I keep coming back to that our role as designers and architects can be to continue to advance and demand and push and find ways to make it work, to specify what products out there, look for other options. I do get I get some optimism from the fact that each year there seem to be more DIY companies that are bringing product to the market that make an option available for a straw-based MDF or for some kind of brass-based plywood that you didn't have before. Whether it removes the open source, that's another complicated question, but hopefully the demand that we as designers bring to the world will move in the right direction, even though it's not going to be a clean and simple path. So.
Hello. This is directly related to the conversation that we're having. my grandma has told me about the CCC, which is the Civilian Conservation Conservation Corps. That was a program that happened in the 30s and 40s, 1930s and 40s, to a relief program for people after the Depression who did not have jobs. There's a lot of people looking for jobs right now. And I think, well, just looking at the buildings that they made during this time, it's a lot of like lodges that you see on national parks and cabins and residential homes that were made of natural local materials, which is exactly what you're talking about. I think we're headed into similar times, and it's very important to look to the past and what they did in the past. And this not only gave people jobs, but it created beautiful architecture that has lasted so far beyond like this American construction that we're talking about. So I guess my question would be like, what role does the architect have in kind of pushing this, like civilians maybe don't have the training, but can we train them? And maybe they have jobs in planting trees, or like people need jobs. And we have all these regulations and qualifications that restrict that. But should we move in another direction?
I'm going to answer your question maybe a slightly different way, which is to me, one of the important roles of architecture is to continue to advocate for innovative design. I still think that the seduction, the qualities, the invention that comes from design is really crucial. And to that end, I would argue that you would not want to set up a kind of binary where working with natural materials is only limited by what we've done in the past, which is to say we can learn from traditional techniques, from kind of ways that things have made, but they shouldn't be somehow the end, right? And so I don't want to kind of position innovative architecture as somehow an anathema to that, nor do I want to somehow say that plant-based materials have to return to some kind of existing model. And so it's really, how do you move between those two? How can the knowledge-based and the skill sets and things we can learn from that be still challenged and advanced by how we could rethink design and material assemblies through creative practices, right? And that, I think that's where things get really, really exciting. The whole question of labor is there. I think it's that. For me, one of the fundamental things is that working with materials that are simply not toxic just makes the act of a construction site better. It plays a huge role. I've spent way too much of my life doing drywall painting with latex paint and working with fiberglass insulation, and I will never do any of those three again, hopefully. So. And yet there's other much more interesting ways to advance just what you do and how to do it and what a job site should be. So.
Great. Thank you, Paul. So we're at time. So I have 4 quick thank yous. First of all, thank you for your journey here, for the lecture, for sharing all of this work. That's 1. 2, thank you for the amazing exhibition that we're all about to enjoy and spend time with. People who are going to go straight into the gallery opening from here. But that's 2. Number 3, if you were a student who helped put up that exhibit, could you raise your hand? Thank you so much. Really appreciate that. And then 4, I just want to echo what Professor Vandergoot said. Thank you for putting these amazing resources into the world and making it accessible to our discipline, for engaging in this conversation. These are fantastic resources. I feel like we should be handing these to students as they come in the door at school. Just here, read that. So thank you for all of that. Paul Lewis, over here.